Hello, welcome to lecture number 14 of CS531 Memory Systems and Architecture. So today we will discuss hardware securities, mainly the security issues in cache memory of multi-core processors. So this is the area where my PhD student Jaswinder Kaur is working. So the presentation that I'll show you today is actually her presentation. She has designed this presentation for her comprehensive Viva. So I'm using her slides for this today's lecture, as well as tomorrow's lecture. Also, I'll use the same slides. So before starting today's lecture, let me discuss something about the NSEM examination and class tests. So I hope you have already received some mail from academic section regarding the new rules of conducting NSEM and class test. To be honest, I am also a little bit confused because they have sent multiple rules in last 1 month for conducting NSEM and class test. So I'll try to understand the recent rules, and I'll send a separate mail within 2-3 days regarding the complete evaluation plan of this course. I hope you are following my lectures and preparing for your NSEM. I'm also assuming that you are working properly on your term paper, because both term paper and NSEM are very important for your final grading. Also, I have already informed you that this is the second last lecture for this course. After today's lecture, there will be one more lecture I'll upload tomorrow, and then I'll finish this course. I hope you understand the basic concept of memory technologies from this course, and I'm assuming that with this knowledge, you will further continue your research in this area. So let's start with today's lecture. So we are discussing today security issues in cache memory of multi-core processors. So one of my PhD student, Jaswinder Kaur, is working in this area, and the slides I'm using here are actually hard slides. She prepared these slides for our comprehensive Viva. I'm using this slide for today's and tomorrow's class. To understand the concept that I will discuss today and tomorrow, you only need the basics of cache memory. That is, what is associative cache, what is hit, miss, what is bank. All this basic information will be enough to understand these two lectures. So I'm sure that you can understand this diagram easily. There are multiple cores. This is core 1, this is core 2. Each core has private L1 cache, and both the cache cores are sharing the last level cache. Here the last L2 is the last level cache, and it's a set associative cache. Also, I am assuming that you understand the mappings in a set associative cache, that which means that if we want to map a particular block in a set associative cache, then first of all we will find the set index, and based on this set index, a block always maps to a fixed set. So this is easy but important concept for today's discussion. I am also assuming that you have the basic idea of replacement policies, when to replace a block. To be frankly speaking, only understanding LRU replacement policy will be enough to understand the basic concept. Regarding the attack, there are two different type of attack possible: side channel and covert channel. So I'll first discuss side channel. The side channel attack is mainly based on cryptographic algorithm. I hope you know the basic cryptographic algorithm. One of the most popular cryptography algorithm is called AES encryption, which is used by most of the application in today's world. So it has been found that no matter how much secure this AES algorithm or the software that we design with AES encryption are, when we run this software on a computer having von Neumann architecture, where there is a cache memory as well as main memory, there is a chance to leak the information, the encryption key. And if there is a leakage in information key, it is very easy to decrypt the information. Because how this encryption key works, because assume there is a plain text to you which you want to send from source to destination, then source will encrypt this plain text with the encryption key, and then the encrypted message will be transferred through the communication channel, and then at the destination again that encrypted message will be decrypted based on a encryption key. So if there is a attacker who know the encryption key, then the entire encrypted message can be decrypted, and it will attacker can get the actual plain text. So so this is the challenge when we run a secure software in a computer architecture. You can understand the problem, that there is no issue with software, there is no issue with encryption technique, but when this same encryption algorithm is running on a one Neumann architecture or running in a computer, there is a chance to leak or the steal the encryption key, and that we will discuss today, and this is called side channel attack in computer architecture. The attack is possible in both single core and multi core architecture. So in this architecture, let us assume that this is the core one where the victim application is running. That means the application where the AES encryption algorithm is running, and the another core, that is core two. This core is running an attacker application whose only intention is to steal the encryption key of the application which is running on core one. And from the architecture, you can easily see that both the core are sharing the set associative last level cache. So the attack or the side channel attack that I will discuss today is based on this shared set associative cache. Because of this shared set associative cache, the attack is possible here. I'll not explain you in detail about how the attacker is stealing the encryption key from the victim application, because if I try to explain the complete policy, then it will take 2 3 lectures. I'll share a paper from 2005, which is the first paper where this type of possibility of this type of attack is explained. You can read this paper if you want to clear the concept. The complete understanding of side channel attack is not required for this course. Now I'll explain you a statement, and based on this statement is enough to understand the lectures that I will cover from this case security part. And the statement is to steal the encryption key from the victim application. The attacker only needs to know the access pattern of victim in the cache memory. By access pattern, what I'm trying to explain here is that suppose if the attacker knows that which set and which block or which way the victim application is recently accessed, then based on this access pattern or the information of access pattern, attacker can retrieve the key. So the question is how from this access pattern the attacker can retrieve the key. So this particular concept I'll not explain here. That's why I said I'll not explain it explain it in detail. So if you want to understand this particular concept, then read the paper of 2005 that I'll share. A simple logic here that I can explain it. Most of the encryption technique, basically the AES encryption, use some pre-calculated table to for encryption as well as description, and these pre-calculated tables are stored in cache memories. So, and if attacker knows the access pattern of this pre-calculated table, that means the which particular location of this table is being accessed by the victim application, then based on this pattern, attacker can guess the key. So since these tables are stored in cache memories in a particular location, so if the attacker knows the access pattern of the victim application in the cache memory, then from this access pattern it is possible to retrieve the key. So the main point that we'll discuss today is how a attacker can know the access pattern of victim. So a possible way to do this is by measuring the time difference of cache hit and cache miss. So suppose the a core requested for a block, and when the block will be received by the core, it can measure the time required to access the block. That is called cache, the memory access time. If the memory access time is low, that means the block was a hit in cache. If the memory access time is high, that means there was a miss in the cache, so it has to access main memory to fetch the block first of all in the cache, and then it has been transferred to the core. So based on this time difference of accessing a block, a core can or an application can easily understand that whether it was a hit in the cache or it was a miss in the cache. And that information is very important in terms of side channel as well as covert channel attack. So if you see that the attacks are based on the time difference of cache hit and cache miss. So how to measure the time? To measure the time, there are different techniques. The two techniques we'll discuss today. One is called prime proof and fast reload. These two are the techniques based on which you can measure the time difference of cache hit and cache miss. And what are the different types of attacks possible? There are different types of attacks possible, but we'll discuss only two types of attack. One is called side channel and another is called covert channel attack. The basics of side channel attack I have already explained to you. I'll again discuss both the side channel as well as covered channel after 2 3 slides. But now the most important point is how a attacker can know the access pattern of victim, because these information is required for both the attack side channel and covered channel. And as I said that this information can be retrieved by different measuring technique based on access time of cache, either it is a hit or miss. So the two access pattern measuring technique that we will discuss today are prime probe and flash reload. So there are two techniques that we'll discuss. First one is prime probe, and then we'll go for flash reload attack. So both are very simple to understand it. Only the basic knowledge of cache is enough. So assume the same scenario here. There is two core one and core two. The core one is running the attacker application, and core two is running the victim application. Now suppose the attacker wants to know the access pattern of set 1 and set 2. That means whether the victim application is accessing set 1 or set 2 or not. In this case, the complete attack is only targeted to set 1 and set 2. And we know that in a set associative case, if we know the block address, then we can easily find out that this block will map to which particular set. So when the attacker will request for a block, it will only request for those blocks which are residing either in set 1 and set 2 in his prime phase. So what attacker will do? First of all, attacker will send some request to this set. So first time there will be a miss in L1 as well in L2. So the blocks will be fetched from main memory and placed here in set 1 and set 2, and some blocks will be some blocks will be here also in L1, right? So this part is clear. This is called prime phase. In prime phase, the attacker will target some set here, set 1 and set 2, and it will request some blocks which are mapping to these two set 1 and set 2. And at the end of this prime phase, all these blocks which is requested by the attacker will be stored in these two set 1 and set 2. This is called prime phase. After prime phase, the next phase for the attacker is probe phase. But before probe phase, starting the probe phase, it will wait for some activity performed by the victim application in these two sets. Because as I said that here the attacker is trying to find out whether victim is accessing these two sets or not. Hence, after its prime phase, it will wait for the victim to access these two sets. A very important point I forgot to mention is that in case of prime probe attack, the attacker and victim are two independent applications. They no need to share any data to perform this measurement. So suppose after the prime phase, victim requests for some memory blocks, and those memory blocks are also mapped in set 1. So what will happen? There is no space here in L2 case. If you see here, this is the LLC, and if you see the set number 1, there is no space left. Everything is filled by the blocks of attacker. So if victim wants to victim requests some memory blocks, and these blocks also maps to set 1, then what will happen? We have to remove some block of attacker and place the victim's block. It will this situation will be transferred to this situation after victim request for some memory blocks. That means we'll remove some blocks from this. Suppose victim requested for 4 blocks, then the 4 blocks will be removed from attacker blocks will be removed from here, and in place of attacker blocks we will place the blocks of victim here. But to do this, one more thing we have to do, because suppose if we remove some attacker block from last level cache, then if we want to maintain the inclusive property of cache, then we have to remove those blocks from L1 cache also. That part I have explained in class, that if we want to maintain inclusive property, then if there is a block in L1, then that block must be present in L2. So if I am removing some block from N2, then that block must be removed from L1 if they are in L1. So there will be invalidation message sent to L1, and the blocks will be removed from L1 also. So now after this, after some time, attacker will again start the next phase called probe phase. So in probe phase, what attacker will try to do? Attacker will try to access the same blocks again. So I hope you remember prime phase. Let me explain you the prime phase again. In prime phase, what the attacker did? Attacker requested for some set of blocks which are mapping in set 1 and set 2. And after this request, all these blocks are placed in set 1 and set 2. And after this, victim try to access the some blocks which are also mapping to set 1. So it replaces some of the attacker blocks. That's it. So now In probe phase, attacker will again try to access those blocks which he accessed, requested or accessed during the prime phase. So if the attacker do this again, what will happen? For all the blocks which are residing in set 2, everything will be hit in LLC. But in case of blocks which are residing in set 1, 4 blocks will result cache miss because these blocks are now removed by the blocks of victim application. So this will be the scenario after the pro phase, that in set 1 there will be 4 cache miss and 4 cache hit, because these 4 will be hit but these 4 will be miss. And in this set there will be all hits, there will be 0 cache miss. So you can see that the access latency of set 1 will be very high because there are 4 misses, and total access latency of set 2 will be very less. So based on this time difference, attacker can easily understand whether which set is accessed by victim. So in this situation, it is very clear that when attacker will find out that okay, the access latency of set 1 is very high, means that victim access the set. So as I mentioned at the beginning, that for attacker, if it wants to leak the encryption key from the victim application, then it is enough to understand the access pattern of victim application. So the prime proof, based on prime proof, the attacker can measure or attacker can understand the access pattern of victim application. Okay, so this is called prime probe attack. Now I'll explain you the flash reload attack. So in prime probe attack, I said that the core 1 and core 2 are running a complete different application and there is no shared data. But in flash reload attack, what the necessary condition is attacker and victim must share some data. So first, what attacker will do? Attacker will the first phase is called flash phase. So in flash phase, attacker will flash all the information from set 1 and set 2 using a CL flash instruction. So after flushing out the data of set 1 and set 2, the attacker will wait for the victim to do some activity. Assume that the victim has requested for some blocks and now these blocks are stored in set 1. Again, remember that both victim and attacker are sharing some data, and the data that the victim has recently accessed and now stored in set 1 are the same data that attacker also shared. Now in the reload phase, attacker will try to access the same set of data that the victim recently accessed, or maybe some more data which are mapping to set 1 and set 2. So if when attacker will request for the data from set 1 and set 2, in case of set 2, everything will be a cache miss. So all the data has to be brought from main memory. So it will take more time. But if we see in case of set 1, half of the data are already there because victim has already fetched the data and now stored in the last level cache. So the blocks which the attacker will request in reload phase, which are mapped in set 1, half of them will be a hit in cache. So if you see that the access times of set 1 will be much lower as compared to the access time of set 2. So in this way, attacker can easily identify the access pattern of victim. So in this case, the set having low access latency is the set which the victim application has recently been accessed. So again, here the access pattern of victim is being exposed to the attacker. So now we'll, based on this information, we'll try to understand cache side channel attack again. So at the cache side channel attack, when I explain you cache side channel attack, what I said that for attacker, if the attacker knows the access pattern of victim, then it can steal the key. How it can know the access pattern? If the victim attacker can know the access pattern based on any measuring technique. And what are the measuring technique that I have explained today? Prime probe and flash reload. Flash reload attack is not very practical because when a secure application is running in a core, it will hardly share any data with another application, which is not very authentic. So reload is not very practical. But if you see the prime probe attack, where the two application can run in two different core without sharing any data. So the prime probe attack is still possible in case of two independent application running in two different cores. Also, it is not necessary that the two application will run in two different cores. It is also possible that both application are running in a single core and they are sharing this core. So we all know that a single core in a single core, two processes can run concurrently, and in this case, both the processes will share the same L1 cache. So the same attack that we are discussing in the shared LLC is also possible in a shared L1 when two application or two processes are running in same core. Hence, the similar attack is also possible in single core architectures. I'm not explaining all these techniques of flash reload and all in detail because it will take more time. What I am expecting from your side, for example, purpose is you should know what is called prime probe attack. You should know what is called flash reload. Then you should know what is side channel attack, what is called covert channel. All these basic concept you should know, and that will be enough for your exam. So in this slide, we will try to understand what is called covert channel attack in cache memories. So you can see there are two applications running in two different core. This assume that this is core 1 and assume this is running in core 2. And also assume that core 1 is a very secure core and it's normally all the secure application runs in core 1. And there is no direct communication possible between core 1 and core 2. But unless in this particular situation, the Trojan application is running on the secure core 1. And Trojan application knows some very secret information, and this Trojan application wants to send or leak this information to the spy application, but direct information sharing is not possible. So what did these two application Trojan and spy will do? They will create a covert channel communication, and through this covert channel they will communicate this secret information. So in this slide, we will discuss how this type of uh, communication is possible through this covert channel. So the any information that Trojan knows, this information must be in a binary format, or you can say that any information in computer is a string of binary one and binary zero. So if there Trojan can send binary 1 and binary 0 at a particular step, then repeating the same step again and again, it can send the entire information to the spy. So in this slide, I will only try to understand that how Trojan can send binary 0 and how Trojan can send binary 1 to the spy. And again, assume that Trojan is running in a secure core, that is core 1, and spy application is running in another core which is not secure, is called core 2. So now there are different measure technique that through which the covert channel can be established. We will go for prime probe measuring technique. The prime probe technique I have already explained. So to start the prime probe attack or prime probe technique, both Trojan and spy must have some initial understanding. So based on this initial understanding, they should know that which particular set in the shared set associative cache should be targeted by both. So they will fix a particular set before starting because they must have this type of understanding. So at the start of prime phase, the spy application will load its own data to the set. So you can see here, after at the end of prime phase, all the blocks here in this set are from spy application. Fine, this part is clear. So prime phase is done. After prime phase, the rest is dependent on Trojan. If Trojan wants to send 0, it will do some activity. If Trojan wants to send 1, then it will do some another activity. First consider if Trojan wants to send 0. If Trojan wants to send 0, it will not do anything actually. It will not do anything. If it has not done anything, it is not requested for any block which is maps to this particular set, then the content of this set will be remain same. So see here. So if Trojan want to send 0, Trojan will not do anything. It will remain same here. But if Trojan wants to send 1, then it will request for some blocks which are again mapping to the same set. So if Trojan request for some block which are mapping to this set, then what will happen? This set has no space currently, but now Trojan is requesting for some blocks which are also mapping in this set. So what will happen here that the blocks from this file will be replaced by the blocks for Trojan. So this will be the situation. So you can see the two different activities, right? If Trojan want to send 0, Trojan is not doing anything. If it is not doing anything, then the content of this set will remain same here. But if Trojan want to send 1, then Trojan is requesting for some blocks which are also again mapping in this same set. So and in this situation, the content of this set will change from SSS to TTTT. That means these are the blocks from Trojan. So now, based on these two different activity, how it is possible to transfer binary 0 and binary 1? It depends on again the same. So in during the prime probe explanation, what I said that by prime probe it can easily understand it. It is possible to understand that whether a particular application is accessing a particular set or not. So and this is the same way. Here, the spy can easily understand that whether Trojan is accessing this particular set or not during its probe phase. Here, this was the prime phase, and after prime phase, if Trojan want to send 0, Trojan will not do anything. If Trojan want to send 1, then Trojan has changed all this block here. So now the probe phase start. During the probe phase, spy will again request for the same four blocks that it has been requested during the prime phase. So if the spy requests the same blocks again, so if in this particular stage all these four blocks will be hit in this cache, that means access time will be less. But if Trojan already converted this cache to this state, and now spy is requesting for the same blocks again. Then all four blocks will be missed in cache. That means the access time of this set will be very high. So based on this time difference, whether the access time is less or access time is high, these two time difference it can easily differentiate two different state. If access time is very less, that means state 1, that means binary 0. If access time is very high, that means state 1, that means binary 1. So through this indirect method, Trojan can send information either binary 1 or binary 0 to the spy. So if there is a information which is string of binary 1 and binary 0, so repeating this step again and again, a complete secret information can be passed from Trojan to spy through this covert channel communication channel. The both side channel and covert channel attack are dangerous for cache memories, and there are a lot of research going on both how to handle these two attacks. But if you see that the main part is same for both attacks, that the timing difference of cache. So how to prevent this for attacker to measure this timing difference is the main challenge. So in normal cache memory, you cannot prevent the timing difference. But suppose somehow if we can internally change the mapping, and we can confuse the attacker to whether there is a hit or miss, then maybe somehow we can reduce it. For example, suppose here both this Trojan and spy know that this is the way, and if this spy will request for four consecutive blocks, then the entire set will be filled up by the blocks of spy application. And now if Trojan requests four consecutive requests from his application, then all these four will be replaced by this T, these blocks of this Trojan. But somehow, if internally this policy can be changed in such a way that these type of actions cannot guarantee that the complete blocks from S will be removed, then somehow we are confusing this Trojan and spy. So there are different kind of solution possible based on which we can confuse the attacker to measure the time difference. So we'll discuss some interesting paper tomorrow, and then we'll stop this because this detailed discussion is not possible. So again, I'm saying that what I'm expecting from your side is just to understand what is prime proof, what is flash reload, and how to perform side channel and how to perform covert channel attack. That will be enough from today's lecture. Tomorrow I'll try to explain two interesting and easy paper. So I am only expecting from you to understand the first paper and not the second paper. So I'm stopping here today. Take care. Bye.